Good afternoon, eights. I checked out your guys' morning work. Generally, the people that submitted generally are doing great. Significant amounts of people need more time, but a lot of people were into like the last section, so I think they'll finish pretty quickly, which is perfect because you're ready for the next step. And the next step is I have one more piece to add about translations, rotations, and reflections. These are the three transformations you guys already know. Just one more piece to add. It's really about the notation. And then I have one more transformation to add. So we'll have a fourth one, which is dilations. And you will see when we add it why it's saved for last. These three are all static transformations. Dilations is not a static transformation. And you'll see what I mean in a few minutes. So first, let's look at the one piece I have to add about translations, rotations, and reflections. Notations for rotations and reflections. Well, we're used to notation for translations. So let's start there and then we'll extend to these other rotations and reflections. There are two types of translations two types of notation for translations. The first type is vectors. And you can see this when we had these two ideas. We use kind of the spiky brackets or pointed brackets for a row vector in this case. And we've also seen column vectors. So we call them row vectors and column vectors. They're both types of arrays, and in some branches of mathematics, the difference between row and column vectors can be massive, actually. It's great adding a second dimension to your numbers because it allows so many more applications. So it depends, but this is like linear algebra are the college classes you would take that use this type of idea from the beginning. It's also really common in physics to use these type of notations for vectors. In pure math, we oftentimes use mappings instead, and you'll see it's because vectors work really well for translations, which makes sense. They're starting at some place, they move to another place, but they literally just like, whatever, this stuff is here and it moves down here and that's it. It's a vector the way it moves. But rotations and reflections don't move that simply. We can't just describe it with a vector. We can use mappings. So you'll see notation for rotations, we can use a mapping. Notation for reflections, we can use mappings. So we're going to use these type of things often today, but it's going to look different. We're not going to be adding to both coordinates like we are in a translation because they're different types of motions. So mappings will work. We're going to look at some and see what happens in both cases. And the rules are easier for rotations when the mirror is one of the axes, either the X or Y axis. The rules are easier for a reflection when the center is the origin. So those are the ones we're going to look at, and they're really the ones that I care about in terms of knowing how mappings work. So let's look at them. Notation for rotations. That should say reflections. Sorry. Let's just change it now. Reflections. You can see, and also I meant to draw in, this is triangle ABC. I was going to make these prettier, but now that we're all here, this is triangle, that one, triangle, and this is triangle A prime, B prime, or A prime prime, B prime prime, C prime prime. Good. So starting with the red triangle here and reflecting in the y-axis. So if this y-axis is our mirror, then this red triangle would reflect through the mirror and get the green triangle, A prime, B prime, C prime, which is good. Starting with the green triangle, A prime, B prime, C prime, if that is our pre-image, and then we reflect in the x-axis here, then when we reflect that down, we get an image down here, which is the blue triangle A prime prime, B prime prime, C prime prime. So following point A and reflecting in the y-axis, I get point A prime, and I've put the coordinates there for it. 1, 2 goes to -1, 2, because 1, 2 here goes to -1, +2. If I follow A prime and reflect in this should say x-axis, should have proofread my stuff. Then we get this A prime prime, and again I put the coordinates. -1, +2 goes to -1, -2, and you can see that reflected here. So we can take that one point that we followed through and look and find general rules. If this point 1, 2 goes to -1, 2, well, the only thing that changed is the x value became the negative x value. That y value didn't change at all. 2 is still 2, so y is still y, but the x value becomes negative. And we see a similar thing here. The x value stays the same, the y value flips. So x goes to x, y goes to -y. And this gives us the two generalized rules for reflection in the axes. These would be nice rules for you to just, in general, remember how they work. I wouldn't say memorize. They should be things you can rationalize rather than memorize. The rotations are a little bit more enigmatic, but they're similar. If I go 90 degrees clockwise or 270 degrees anti-clockwise. So starting here at A, 90 degrees clockwise gets me here. Oh, with a center at the origin, I should have said that. 90 degrees here, or I could take A and I could go 270 around this back way anti-clockwise and I get to the same place. 180 degrees, if I start with the red A and go 180 degrees around, I get to the blue A prime prime. It doesn't matter which direction I go, I get there. And then 270 degrees clockwise, if A goes around 270 degrees, I get to the pink A prime prime prime. And if I go 90 degrees anti-clockwise, I get to the pink A prime prime prime. So just saying these are the same rotations, and so they should have the same rules. So going from the red to the green, if I go 90 degrees clockwise, I can see the point 1, 2 became the point 2, negative 1. And if I go 180 degrees, I can see 1, 2 became negative 1, negative 2. If I go 270 degrees, I can see the point 1, 2 became the point negative 2, 1. So again, that gives us rules for how these work. Just follow this through. Well, this x coordinate here moved over to the y and became negative. So that x will move over here and become negative. And this y coordinate just became the x coordinate. So this y coordinate here becomes the x coordinate. That's it. Same thing here. You can see x just becomes negative, y becomes negative. So x becomes negative, y becomes negative. And here that x coordinate went to the y coordinate and the y coordinate went to the x coordinate and it became negative. And so y coordinate goes to the x coordinate and becomes negative. X coordinate goes to the y coordinate. But you can see if you just look at one point and think of the way they go, you can rationalize the way these are. So I wouldn't say you need to memorize these. You do need to understand how mappings work. So that's my notation for rotations and for reflections. The last piece we need to add is this one last idea of dilation, or the other name for it is enlargement or reduction. It'll be easier for me to talk about it here. So if I clear this, if I start with this triangle, we've got the same triangle that I had before. So the point A is at 1, 2 like we're used to. And you can see we can do translations. These all work normal. Reflection over X and Y axis, like I could just do, this is what I did to come up with those things. Clear it, draw it. I can rotate things, great. I can also dilate. So let's look at what this looks like. If I dilate by a scale factor of 2 around the origin, oh, and I forgot I need my drawing tools. So around the origin, what happens is you see the point 1, 2 goes to the point 2, 4 because we have a scale factor of 2. So if A was at 1, 2, then A prime will be at 2, 4 because the scale factor is 2. So just saying that the coordinates get multiplied by 2. What else do we see? You see the distance here, not at a certain distance. Well, this distance is twice as big. So that's all we have to do with dilations, is that things will either enlarge or they will reduce. The difference between dilations and the rest, and you can see it, is that dilations are not static. This triangle we started with is not congruent to the triangle we ended up with. It is similar. That's the word for it. These are similar triangles. They have all the same angles, but the edge lengths are different. So good, we've got similar triangles. And you can see when the scale factor is large, the triangle is going to get bigger. That's why sometimes we call this, we call it enlargement. But sometimes we also call it reduction. So why would it be reduction? Well, let's come back here and look at another example. What if instead of a scale factor of 2, I used a scale factor of 3/4? Oh, it doesn't like division, so I'll do 0.75 for 3/4. Let's clear this, draw that triangle, dilate. When we dilate by 3/4, you see all of these coordinates became smaller. Well, if we use that same rule we had before, and again, I should say, this is only a true rule for dilations around the origin. When the origin is your center, this will work. We had the point A was at the point 1, 2, and we dilated, our scale factor was 3/4. So the point A prime should be 1 times 3/4 is 3/4. 2 times 3/4 is 6/4, which is 3/2. And if I look here, that point does look like the x coordinate is 3/4, y coordinate is 3/2. So that is the way it works. You can see when the scale factor is below 1, it'll come closer to the origin. When it's bigger than 1, it's going to go away from the origin. And I could show you just to point out the obvious. If I clear this, draw that, what happens if we have a scale factor of exactly 1? So if I take the point A, 1, 2, and I multiply by 1, I still get 1, 2. So when I dilate, it's the exact same size. These triangles are congruent exactly when the scale factor is 1. That's the only time they're congruent. So those are the new things I had for you 8s. There is an assignment below dealing with dilations, and just look at the LMS and it'll tell you which problems I expect you to do. As always, let me know if I'm unreasonable. I know there are some people that still have to finish the morning assignment, but most people were pretty close to finished already. So if I'm unreasonable, shout out to me. Otherwise, best of luck. I'll see you guys soon.